Hi everybody, Dr. Ricardo. This is the third video for chapter 13. We're starting on page 10 of the notes. So we're going to dive into the four colligative properties. The first one is vapor pressure, okay? And we can look at it two ways. We can talk about it in terms of delta PA, which is the vapor pressure lowering, or the second way we're going to look at it is actually go right to calculating what is the vapor pressure. So you either can know what the old vapor pressure is of the pure liquid, figure out how much it's lowered, and then subtract it off from the pure. It's always going to be lower, right? Or you can use a formula to just give you directly what's the vapor pressure once the solute is added. So remember, the colligative properties are when you add a solute to a liquid, you change the properties of the liquid. And it's not a function of what you put in, just how much, just how many moles of stuff you put in. So I consider it like junk. Once we start adding junk or contamination to the liquid, that junk is going to hinder the liquid's ability to evaporate. The wrong molecules are going to be stuck in the way, right? So the molecules can't get to the surface and escape because this junk is in the solution. Okay, so vapor pressure lowering is going to be called delta PA. A is the component that we're interested in. Delta means change in the vapor pressure. How much has the vapor pressure changed by adding component A? So delta PA of a solvent is equal to the vapor pressure of the pure solvent minus the vapor pressure of the solution. Okay, here's pure. We put the little zero on it. So how much has the vapor pressure been lowered? How much does it go down? How much has it changed? That's what delta means, change. I look up the vapor pressure of what the pure solvent is, and I subtract off the vapor pressure when I have the solute molecules dissolved. Okay, so here's the definition of everything. We're always going to be working at constant temperature. Can't be changing the temperature at the same time that I'm doing the rest of the experiment. So at constant temperature, what is the effect of adding junk to the solution, adding an impurity to the solution? Okay, so again, delta PA is the vapor pressure lowering of A. Okay, so A is the solvent. So the vapor pressure, let's pretend we're talking about water. The vapor pressure lowering of water is equal to the vapor pressure of pure water at that certain temperature and pressure. Okay, and at a certain temperature and external pressure, and the PA is the vapor pressure of water after you've added the junk to it, so in the solution. Okay, but let's do a practice question, or let me go over this first, then we'll do a practice question. I have a non-volatile solute, okay, it's going to reduce the rate of evaporation of the solvent. So here's the pure solvent. Okay, so all the molecules are the same. There's no junk in it. Here's the solution. Those darker or colored in guys are the impurity. Okay, so once I put those guys in there, what happens? They can't evaporate because they're non-volatile, right? They have a very high molar mass. They're not going anywhere. There's something like lead or salt or sugar, right? It's only that these guys that aren't colored in can evaporate, okay? So here's the rate at which they evaporate. These are the evaporation. This is the recondensation. You see, once the solute gets in there, the rate of recondensation is going to be the same, but the rate of evaporation is going to be less. Okay, so if I put these, this is really kind of cool. Why is the re-evaporation going to be less? Because these guys are blocking the sites, right? If this guy down here is headed up in the right direction and has enough kinetic energy to escape, he might hit one of the solute molecules and therefore he can't escape. So they're kind of blocking the path of getting out. Okay, so if I put a glass container over these two things and have them side by side, one is pure and the other one is a solution, what's going to happen over time is amazing, right? So again, cover this whole thing with a glass bubble, is that since these guys are coming up and down at the same rate, but these guys are reprecipitating or recondensing at a higher rate than they're going up, eventually all of this will work its way over to there and this one will be empty and you'll wind up with a homogeneous solution versus a heterogeneous solution versus a homogeneous solution. So things naturally mix. There's no energy driving force for this. It's just an entropy force, right? But that is pretty amazing to me that you put two beakers next to one another. Now, if I leave this open to the environment, they're both going to evaporate and I'm not going to see anything. At the end of a week, all that I'm going to have is the non-volatile particles down at the bottom. But if I cover this, right, so that there's nothing can get out of the whole bubble. Okay, I don't want to draw my picture, but just picture this covered with a bubble, right? Bubble goes over the whole thing, right? So picture that. I close this up. Oh, I could do it like that. Okay, close this up. So the whole thing is covered up, right? This is totally inside a bubble. So there's the bubble. It's covered with glass. Well, these guys are going to come out of here and go up into here, and this is going to become saturated with the solvent molecules that can evaporate. So this is going to be saturated up here. Right? So that's the gas that's saturated with the liquid. But eventually, you see how everything winds up over here because these two arrows are the same. But this arrow, the down is bigger than the up. So they're going to wind up, everything is going to be over here. Pretty neat experiment. Good. Okay, let's talk about Raoult's law. Raoult's law is the formula that you're going to use to calculate the new vapor pressure of the solution if you know how much of the non-volatile solute has been added to the solution. So it's very simple. To find the vapor pressure of a solution containing non-volatile solutes, the vapor pressure of the solution, okay, is equal to the vapor pressure of the pure solvent. So this would be the vapor pressure if you were doing water. This would be the vapor pressure of pure water at that temperature times the mole fraction of the solvent, of what it is that is evaporating. Now, think about this. If this number is 1, you have a totally pure liquid, right? It's all water. You haven't added any impurity at all, and that makes sense. 1 times the vapor pressure of the pure gives you the vapor pressure of the solution. Well, the solution doesn't have any non-volatile stuff in it, so these two numbers should be the same. If it's 0.5, right, then the vapor pressure will be half. Well, that kind of makes sense, right? It's going to be half as high as it would be if it was pure solvent, okay? So remember, X is bound, right? X has to be someplace between 0 and 1. 1, when X is equal to 1, you have pure water, pure solvent. When X is equal to 0, you don't have any water. Well, guess what? If you don't have any water in your solution, how can water evaporate? So 0 times whatever the vapor pressure of water is going to give you 0. And then you have all the different places in between. Okay? So X of A has to be less than or equal to 1. Okay? And has to be, can't go below 0 either. Okay? So very simple formula. That's all you have to do. So we'll practice in a bit. If I have a 2-component system, so what do I mean by that? In a 2-component system, I only have A and B, where A is the solvent and B is the solute. Excuse me, I have to sneeze. Okay. So A is the stuff that we're interested in, the solvent, and B is the other stuff. Well, again, think about it. Mole fraction is the fraction that's A plus the fraction that's B. So whatever is A is not B. So it is always the case that XA plus XB in a 2-component system is equal to 1. If it was a 3-component system, XA plus XB plus XC would be equal to 1, right? They all have to add up to 1 because in the end, I've got to get the total number of moles of everything. This is the fraction of the moles that are A plus the fraction of the moles that are B have to add up to the total because there's only 2 things. So here's our solution. A is the stuff that can evaporate. B is the stuff that can't. This is the junk. Okay? Okay, well, look what happens if I want to figure out how much the vapor pressure has changed, right? So delta PA is how much the vapor pressure of A is lowered by adding B. Well, this is always true, that delta PA, like we learned before, is equal to the vapor pressure of the pure minus the vapor pressure of the solution. The solution will always be lower than the pure because vapor pressure, by adding the non-volatile solute, you're going to hinder the ability of the volatile solvent to evaporate, so this number's got to be lower than that. Okay? So how much has it been lowered? Take the pure minus the solution. All right, well, guess what we just learned? Let's substitute in Raoult's law. So the vapor pressure of A is equal to the vapor pressure of A when it's pure times X of A. Okay? So I substitute this in for that, and I get this formula. So in there, I just put all that stuff. Okay? Now, when I look at this, I can factor out delta P, P0 of A. So what am I factoring out? The vapor pressure of the pure stuff, that's what the little zero means. And what stuff is it? The solvent A. So I can factor that out. Well, if I factor that out, I get 1 minus X, right? Pull out the PA, I get a 1 over here, and I get an X over here. Well, what is 1 minus X? Well, 1 minus X, 1 minus XA, right? So what is 1 minus XA? Well, that's XB, right? Because rearrange this, XB would be 1 minus XA. So it kind of makes sense. If I want to calculate how much the vapor pressure is lowered, I take the vapor pressure of the pure and I multiply it by the amount of solute. If I want to calculate what the vapor pressure is, not how much it's been lowered, I take the vapor pressure of the pure and I multiply it by the mole fraction of the solvent. So this one is for the solvent, this one is for the solute. Okay, and again, they got to add back up, right? The vapor pressure of how much the vapor pressure has been lowered, plus what the vapor pressure is for the solvent has got to add back up to the pure. Okay? So that's how vapor pressure is lowered. Here's an example. It's always good to do an example. What is the vapor pressure of a glucose water solution that is 0.2 mole fraction in glucose at 20 degrees? So again, they specify the temperature. We're not changing the temperature during the course of the problem, right? That would be unfair. Can't do that. The vapor pressure of pure water I could look up at 20 degrees. Perfectly pure water is 17.5 mmHg. That's a unit of pressure, right? It's equivalent to a torr, right? You know 760 mmHg make 1 atmosphere. So this, at 20 degrees, water isn't really evaporating very much. It's only evaporating 20 torr or 17.5 torr or 17.5 millimeters of mercury. Way different than it is at 100. At 100, it's boiling and it's 760 torr. So this is very low. Okay, it doesn't matter. It is what it is. Okay, what is the mole fraction of water? Well, they told me that, right? They told me the mole fraction of glucose, it's just a 2-component system. I took sugar and I put it in water. So my glucose in water is 0.2. So what isn't glucose is water. So if this is 0.2, what's 1 minus 0.2? 0.8. So that's how I got my 0.8, right? The mole fraction of all of the components have to always add up to 1, and we have just a 2-component system. So what isn't sugar must be water. Okay, so all I have to do to find out what is the vapor pressure of this sugar, of this glucose solution is take the vapor pressure in pure water. This is right from Raoult's law, right from the one from the top of the page, multiplied by its mole fraction. This is unitless, so my answer is going to come out in millimeters of mercury. 2 significant digits, 3 significant digits. Probably should have just left this as 14 point. Okay, probably has 1 too many significant digits on there. All right, so that's an example of using Raoult's law to calculate the vapor pressure. Okay, next thing. For ideal solutions behave, follow Raoult's law under all concentrations, okay? Now, what would be a non-ideal solution? A non-ideal solution would be something like ethanol dissolved in water or methanol dissolved in water, where the two molecules are interacting with each other at a different, to a different degree than they would interact by themselves. So there's a difference in the intermolecular forces. Okay, so in those cases, you're not going to get a perfectly straight lines like I'm going to draw in the graph in a second. But when you have ideal solutions that follow Raoult's law, really all you're doing is blocking the evaporation of the other guy, right, by being in the way. So there's no real chemistry going on. So let's read when solutions behave ideally. Okay, so real solutions best approximate ideal behavior when the solute concentration is low. So if you only have a little bit of solute, it's going to follow Raoult's law very well. Second, the solvent and solute are similar to one another in size and polarity. Okay, so if I mix alcohol and water, they're not that similar, so they would not behave so similarly. Okay, here is an example of two things that behave ideally, so I can show you how they would come out on a graph. And the last thing is if they have similar intermolecular forces. So it's kind of like 6 of one, half a dozen of the other. It doesn't matter. The two molecules are so similar that I can't really tell them apart. Okay, well, that's my example here. If I take benzene, which is C6H6, and toluene, which is C7H9, okay, 3 and 5, H8, okay, and I mix these two molecules together. Remember, this benzene really, you guys didn't learn organic chemistry yet, looks like this, okay, but that's the way that organic chemists save all of this writing, okay. There's your C6H6. So very simply, next year when you take organic chemistry, this quickly just becomes this. Okay? So all of that is expressed over here, where there's the double bond on this one. Okay? So it's kind of like a chain link fence to make benzene, that they 6 carbons, every alternate single and double bonds get C6H6. What's my toluene? Same thing, only over here, instead of having a CH3, instead of having an H, I put a CH3. So that one has this same structure, only replace this H down here with another CH3. So this has called a methyl group hanging off. Well, when I mix these two things, they behave ideally. So ideal behavior would mean, now they're both volatile. This is interesting, right? So they're both volatile. So the total vapor pressure is equal to the vapor pressure of A, let's make that benzene, when it's pure, times its mole fraction, plus the vapor pressure of B, which is toluene, times its vapor pressure. So I can always calculate it using Raoult's law for both. Now, this is kind of neat. Let me show you, for a 2-component system, I can make a cool little graph to show that, okay? So let me, before we go on to boiling point elevation, let me draw this graph for you for a 2-component system. Let me make it a little bit nicer colors, okay? So what I'm gonna have over here is I'm gonna mix benzene and toluene, okay? So over here, I'm gonna have all toluene. Okay, so 100% toluene. So this guy is going to be X, let's call it T for toluene, XT equal to 1. So if I have just a 2-component system and I'm mixing different amounts of benzene and toluene, if I have all toluene, I must have no benzene, right? So that makes sense. So this is all toluene, no benzene. So 100% toluene, no benzene. Right smack in the middle is going to be 0.5 mole fraction of toluene, 0.5 mole fraction of benzene. They're both going to be 0.5. Okay, exactly identical number of molecules. Okay, here, got all of one, none of the other. Here I've got half and half by counting up the molecules. So you could think of 1,000,000 molecules of this and 1,000,000 molecules of that. And here, what's the mole fraction? No toluene and all benzene. All right? I could do this because it's just two components, so I'm mixing the two together. Okay, now toluene has a slightly higher vapor pressure than benzene. Why? Well, look at the molecules. The molecules are a little bit bigger. Okay, I've got that extra methyl group on it. So they're going to be slightly higher. So what I'm going to do then is, let me get a ruler, and I'm going to say, let's let this represent the vapor pressure of pure toluene up there. Okay, so that's the vapor pressure of pure toluene. And I'll give it a number. And let's say this is the vapor pressure, and that's going to be the vapor pressure for pure toluene. Okay, VPT, pure toluene. Okay, here's the vapor pressure of pure benzene. It's a little lower. Okay, so instead of going straight across, it's going to be a little lower. Why? Because the molecules are a little bit smaller, and they're going to be it's going to be a little bit higher, right? The molecules are a little bit smaller, and it's going to be a little bit more volatile. So this is VP0 for benzene. Let me put the 0 means pure. So that's the toluene, that's the benzene. Okay, well, if this is an ideal solution, this line starts at the maximum when it's pure and goes all the way down to 0. Why does it go down to 0? It goes down to 0 because if I don't have any benzene, how can benzene be evaporating? So that's a no-brainer. So this guy's going to go down to 0. Okay, so this is, if I could measure the amount of benzene that is evaporating from the solution at any mole fraction, this is what I would get. Okay, at 0.5, I would get half of the value that I got at 1. Okay? All right. What about the toluene? Toluene, I'll do it in black. Same thing. Here it is when it's pure. So it's evaporating. It's 100%. So it's going to have the same vapor pressure as the pure. If I don't have any, it's got to go down to 0. So if I'm asking the question for my solution, which has both of them in there, right? This is the solution. It's going to have green in there, and it's going to have black in there. Okay, hard for you to see them, different. Okay, it's got both different kinds, and they're going to be evaporating. Here comes a couple of the green, evaporating. Here comes a couple of the black. What is the pressure above the liquid of the black or the green? I could just go across and measure what it is. So this graph is perfectly the same as just using the formula, okay? Because the formula is linear. When you have half, you're going to have half. Now, here's the cool thing though. What is the total vapor pressure of all of them? Well, if I want to know the total vapor pressure when I have a solution that is 50-50, I just add them up. The total vapor pressure would be this amount plus that amount. The amount of the green plus the amount of the black line. What about over here? Let's say when I have mostly benzene, where this is 0.9. So it's mostly benzene, right? And this guy down here would be 0.9, and this guy would be 0.1. Okay? Well then, I would just find out how much this is. That's how much toluene evaporation I have. And that's how much benzene I have. So what's the total of both of the volatile solvents? Just add them up. Okay? Nothing special. This graph is just representing this formula, right? The total vapor pressure of the two things that are evaporating, because in this case they're both volatile, is going to be this one plus this one. Now, why is that important? Think about gasoline. Gasoline has hundreds of different volatile compounds in it. They're all volatile. They have to be volatile because they've got to get into the gas state in order to burn them, right? We have to inject them in to the engine at the right temperature and light the spark so that they can burn. So they have to evaporate. They have to be volatile, right? So if it's hundreds of different compounds, what is the vapor pressure of gasoline? Well, the vapor pressure of gasoline is the sum of 100 of these terms, all of the different molecules are going to provide pressure coming off of the liquid. That's why it's dangerous and explosive. It's the gas in the gasoline that evaporates and burns in the air. But I could take it for benzene plus toluene plus hexane plus all of the different ones to get the pressure, the vapor pressure of gasoline at a certain temperature is the vapor pressure of each one when it's pure times its mole fraction in gasoline. Now, since gasoline is hundreds of different molecules, okay, these X's are all going to be small numbers, right? And what are the big components in gasoline? Not a lot of benzene anymore in gasoline, thank goodness. And the toluene is also low, okay, because these are pollutants. But there's going to be a lot of octane, septane, and all different compounds around from C6 up to about C9 or C10. Every different variety of isomer in there is going to be mixed into the gasoline. Okay, but gasoline pretty much behaves ideally because the molecules are all the same. Okay. Okay, so we finished vapor pressure depression, right? So how much is the vapor pressure lowered when you add a solute? Let's talk about the effect that it has on boiling point, okay? So boiling point is always going to be elevated because when you add the junk, right, you add the non-volatile stuff, it's going to cause the less of the molecules to evaporate. If less of the molecules evaporate at that certain pressure, you're going to have to go to a higher temperature to reach atmospheric pressure. Boiling is defined as the point when the vapor pressure equals atmospheric temperature. So any solute molecules that you add to the solution, that you add to the solvent, are going to lower the vapor pressure and therefore raise the temperature that you're going to have to go to reach 1 atmosphere of pressure. Okay, so if we did normal boiling point elevation, we'd be talking about the boiling point at 1 atmosphere of pressure. Okay, so at 1 atmosphere of pressure, which is what we're feeling in New Jersey, right? We're pretty much at sea level. Okay, so 1 atmosphere of pressure is the pressure we feel every day. All right, so all you have to do, delta TB is how much the boiling point has been elevated. This is going to be a small number like 2.5, 3.5, 4.5. It is the amount that the boiling point is elevated, not the boiling point. Okay, so if I ask you what the boiling point is, you have to take what the boiling point is and then add this number on because it's always going to be positive. It's always going up. All these boiling point constants are positive, and molality is always positive. Okay, so this is the molality of the solute. Okay, so if I add salt to water and I know its molality is 1, I just take 1 times the boiling point elevation constant for water, and I get how much the temperature is boiled. Again, doesn't matter what the stuff is, okay? Just take its molality times its boiling point, okay? So you're just going to look up these boiling point elevation constants for the different solvents. You'll have 1 for water, 1 for hexane, and just do the calculation. So we'll do one in a bit, okay? All right, while the boiling point is elevated, the freezing point of the solution is also depressed based on how much solute is dissolved. The formula looks identical. This time, you look up Kf instead of Kb, get it off of the table. It's the molar freezing point depression constant, and you look it up for each individual solvent. So there'll be 1 for water, 1 for ethanol, 1 for any solvent. Again, we don't care what's dissolved. All we care is that something is dissolved. If nothing is dissolved, this is 0. The freezing point is the regular freezing point. So if we were doing water, we know water's freezing point is 0. So delta TF for pure water. In pure water, I don't have any solute dissolved, so I'd have 0 times the freezing point depression constant would give me 0. Okay? Pure water, if I don't have any solute dissolved in pure water, there's no molality of the solute, so this is 0, times the freezing point depression constant gives me 0. So again, the pure ones will always come out to the same number that you're used to. For water, this is 0. The freezing point of pure water is 0, and the boiling point is 100. Now, remember, if I ask you the freezing point of the saltwater solution, I'm not just asking you to calculate delta F, you have to subtract it from whatever the regular freezing point is. So the regular freezing point for water is 0 degrees Celsius. So if this answer comes out to 3.7, you have 0 minus 3.7, the freezing point of the solution would be negative 3.7. Okay? All right, let's do it. I think this first example is for water. What is the freezing point and boiling point of a solution of 100 grams of ethylene glycol, antifreeze, right, dissolved in 900 grams of water? So I make up the antifreeze solution. It is a 10% antifreeze solution, but first thing we need to calculate is what is the molality of the antifreeze. Well, just out of curiosity, let me show you what antifreeze looks like. So this is what ethylene glycol looks like. Looks like an alcohol, but it's a kind of a double alcohol. Alcohols have OH groups, right? If I just filled this out with hydrogens, it would be methane. Ethylene glycol has got 2 of them. So it is a kind of a thickish material. It's a little oily, okay? And it's these OHs on here that are hydrogen bonders, and that's what makes it very non-volatile, okay? So ethylene glycol has a very low boiling point itself. It does not evaporate. Okay, when we mix it into water, first thing I have to figure out is what's the molecular weight of ethylene glycol. I would have to give you the structure of ethylene glycol, tell you the formula, or give you the molecular weight. So let's see where the 62 comes from. The 62, guys, comes from 12 times 2 plus 16 times 2 plus 1 times 6, right? So you have 6 H's, 2 C's, and 2 O's. If you add all of those up, you should get 62. So that's where the 62 comes from. All right. Again, if I want to calculate how much the freezing point is depressed and the boiling point is elevated, I'm going to need to calculate the molality. So in the numerator, I need the number of moles of ethylene glycol. 100 grams of ethylene glycol divided by its molar mass gives me 1.61 moles of ethylene glycol. Molality is what's used in the formula here, not molarity. You'll get it wrong if you use molarity. So what goes in the denominator? The kilograms of the solvent. 900 grams of water is 0.9 kilograms. So the molality is 1.79 molar ethylene glycol. All right, where did I get this number? Kf for water and Kb for water. They're going to be listed in your textbook, okay? They're independent of temperature, they are just one number. So the molal freezing point depression constant is 1.68 degrees Celsius for each molal. So every molal of junk that I add to solution, my freezing point gets depressed by about 2 degrees. So instead of being 0, it's going to be around -2. Okay, this got a point in it. Okay, all right. How about boiling point? It's less affected. For each 1 molal that I add, I go up about 1/2 degree. So if I have a 1 molal solution, my expectation is it's going to be about 100.5 instead of 100. Well, how big is our solution? How much junk did we put in? We put 1.79. Okay, so how do I use this formula? Very easy. I just take that constant, multiply it by the molal, and I'll have how much the freezing point is depressed or how much the boiling point is elevated. So I did them parallel to each other. I did the freezing point on the left and the boiling point on the right. So here I just plugged in. Again, this number's got to be given to you in the test. Okay? Or you look it up in a book. I'm going to go find them in a second. Okay? So in both cases, I take freezing point depression constant times the molal, boiling point depression constant times the molal. Okay? Here, multiply these two numbers, I get 3.33 degrees C. Right? This is how much the freezing point is depressed. The regular freezing point is 0. Then I have to depress it, freezing point depression. So subtract 3.3. Water ordinarily freezes and ice melts at 0. Not if I put ethylene glycol in it. By putting that much ethylene glycol, I can get it to go all the way down to -3.33 Celsius. Okay? Well, that's the function of antifreeze. Don't freeze the water in your radiator of your car. All right. What about how much would the boiling point be elevated? I'll take my 1.76, which is the molarity, times the constant. It's going to go up by about 1 degree. Water ordinarily, so this is how much it changed, right? It got elevated by about 1 degree. So how much is it? This is F over here, this is B. It's what it usually is plus that amount because it's elevated. So it's about 101 degrees. Okay? So we would expect the range at which an ethylene glycol exists as a liquid to spread out. It goes from -3 all the way to 101, where pure water only goes from 0 to 100. Right? Here's some numbers. Okay, again, don't have to memorize any of these. For water, benzene, and ethylene glycol, here's the normal boiling point. Okay? Here's delta K, Kb. Here's the normal freezing point. And here's Kf. So again, water, we use 100 and 0. If you were doing a benzene question and you figured out how much the boiling point was elevated, and let's say it was elevated by 2 degrees, and I asked you, well, what is the boiling point of the benzene with the solute in it? You'd have to take 80 plus the 2 degrees. Okay? If the freezing point of benzene was depressed, benzene ordinarily freezes at 5.5. If it's depressed by 2 degrees, you have to subtract 2 from 5.5 to get 3.5. So these are your starting numbers. This is the regular temperature at which things boil and melt. So you have to go to very low temperatures to freeze alcohol. Okay, good. Not a function of the solute. You don't see anything over here that talks about the solute. Everything is related to the solvent. Okay, now, next thing that's kind of cool is that if you want to calculate the molality of something, if you have an unknown, right, and you want to calculate the molality, all you have to do is you can use freezing point depression to figure out what the concentration of something is. So you would take the freezing point depression that you measured, divided by the Kf for the solvent, and you could get the molality. Once I know the molality and how many kilograms of solvent I had, I can multiply those two things together to get the moles of the solute. And the last thing I can do with that is if I know the moles of the solute, I can put that in the denominator of this equation. So I can use this technique, freezing point depression, to calculate the molar mass of an unknown solute. Take the solute, right? Take a known mass of it. That's the grams of the solute. Dissolve it in a known mass of a solvent, like water or alcohol. Measure the freezing point of that solution. Then go back and do this calculation. So if I measure the freezing point of the solution, that's delta TF. How do I get? I subtract it from the regular freezing point. I get how much the freezing point was depressed, divided by the freezing point depression constant that I look up, and I get the molality. I know the kilograms of solvent because I took my unknown solute. I didn't know what this stuff is. I took my unknown solute, I put it in a known amount of solvent. So I know this. I know how much water I started with. Right? So I take this molality that came out of here times the kilograms of solvent. That gives me the moles. Okay. I didn't know what the stuff is. It's an unknown, but I know how much I took. I weighed it out. So I take the grams divided by the moles that I get from this equation, and use it to calculate molar mass. So in Chem 2 lab, this is a great experiment that you would get is you use freezing point depression to figure out the molecular weight of an unknown solid. It's a pretty good technique. Okay, you don't know what it is, but you know it undergoes this effect. Very neat. Okay, this is from the old book, so this doesn't really pertain to you, but I bet you there's a question like this in the new book. I'll see if I look it up in a second. Okay, all right. So we have one more thing to talk about. So far, I did vapor pressure, how much the vapor pressure is lowered, boiling point elevation, and freezing point depression. Okay, I did all of those for molecular substances. What happens if the substance is ionic? Well, if the substance is ionic, I have to add one more factor to all of my formulas, okay? Because the substance is ionic, it gives me more than a one-to-one amount of junk, okay, of particles in the solution. Because when it dissolves, right, this is a ionic solid, right, like something like sodium chloride, X's and O's. Here they are dissolved in the solution. When it dissolves, it gives me X dissolved in solution and O's dissolved in solution. So sodium chloride would give me a factor of I equal to 2 because I get 2 particles for each of the salts. So that's really neat. The colligative properties are a function of how much junk is dissolved. So if you dissolve an ionic substance into the solution and it breaks apart, you need to double its effect because it has twice as effective as sugar. Why twice as effective as sugar? Because you get 2 particles for every time it dissolves. If sugar dissolves, you just have sugar solid here, and then on the other side, you have sugar aqueous. So I would be equal to 1. So I, in this case, for a 1-to-1 salt, would be equal to 2. Okay? How about if I dissolved magnesium chloride into solution? What would my I be? Well, magnesium chloride looks like that. If you dissolve this, I is going to be 3. I get 3 particles, 1 magnesium plus 2, and 2 chloride minus 1s. Those are my 3 particles. Right? I get a 3-to-1 relationship. So when the freezing point is going to be depressed, it's going to be the freezing point depression constant for water times the molar concentration of the salt times 3. Because really, I times Cm, the molar concentration of the salt, will give you the molality of all of the ions, because all of these are blocking the ability for the substance to freeze. So I is called the Van Hoff factor. It's the number of particles per formula unit. We just did magnesium chloride. I is equal to 3 for magnesium chloride. Okay? All right, so Cm is the molality computed on the basis of the formula of the ionic compound. So I, you could calculate for I, again, if you had an unknown salt, somehow you knew the total concentration of the salt, you knew the freezing point depression constant, and you measured the freezing point, and the freezing point was turned out to be delta TF. So you have all of this. You can solve for I up here for either freezing point or boiling point. So you also have delta TB is equal to I times KB times Cm. Okay, Cm again is the molality of the ionic compound as a whole. Right? So I times Cm would be the molality of the ions that come from it. Now this is really cool because what happens, sometimes things don't really break apart when they go into solution 100%. We tend to think that the sodium chloride breaks apart 100%. Well, sometimes it doesn't. Sometimes things only ionize to a certain fraction, and other than that, they're dissolved, but they keep some character together. Okay? Well, if I comes out like you expect it when you look at the formula to come out to 3, but it doesn't come out to 3, it only comes out to like 2.7. Well, what does that mean? That means that in solution, you actually have some association between a small percentage of the ions are actually kind of together as little units. So they don't dissolve totally like we think of in Chem 1, right? When ionic substance totally dissolve into their ions. So it gets a little bit more complicated. At very low concentrations, usually these things go all the way down to totally dissolving. But as the solution gets more and more salty, the magnesium chlorides are going to kind of be stuck together and associate together a little bit. You might see that I doesn't come out exactly at like 3 like you'd expect. It comes out more like 2.7 or 2.4 or 2.5. Again, the more concentrated you make the solution, the worse this becomes, the further away you get from total ionization. Okay? If you have only a trace amount of magnesium chloride, it's all going to dissolve the way we learn in Chem 1, all break down into individual ions, and you should expect I to be really close to 3 or almost exactly 3. Okay, so our formulas from before, but I had a simplified version, especially boiling point elevation and freezing point depression, you can stick a little I in here. And I is the number of particles that you get once it dissolves. Okay, so you can put your little I in here and here. You don't have to do that on vapor pressure. Okay, because it's a mole fraction kind of a thing. Just on boiling point and freezing point depression. Okay, these numbers are all in your textbook. I'm not going to look them up now for you. They haven't changed in 10 years. Don't worry, they don't change. Okay, again, I will see if I find a problem like this that you should look up. Calculating using either this or this. These are both cool, right? Using freezing point depression or boiling point elevation to figure out what the molecular weight of an unknown substance is. Okay, let me see if I find that for you in your book. Okay, so that guy, that was, we'll do this question now, and then I'll save osmosis for a separate, video. Okay, so first thing I want to do is from your book, I wanted to see if I could find that kind of question that I was talking about. Okay. So these are all going to be in chapter 13. See if we see an example. Using freezing point depression to calculate the molecular weight of an unknown substance. I'm not seeing it in the textbook directly. At the bottom of page 546, you see the same graph that I had in my notes. Gives you water, benzene, carbon tetrachloride, chloroform, tells you their freezing point depression constants, their boiling point, right? These are the solvents. How much their freezing point is depressed or boiling point is elevated doesn't matter what you put in, but when you put stuff in, it's going to lower the freezing point and raise the boiling point. Okay, this is a good graph. We'll go over this in a lecture. It kind of shows you why the freezing point is depressed and the boiling point is elevated when you add the solute molecules to the solution. So this is what's happening for the pure, and then this is what's happening for the solution. So you see the boiling point is elevated, it's higher, and the freezing point is depressed here. Okay, so I'll go over this when I go over the PowerPoints. Okay, let's do this question then. Okay, the problem that I wanted to do with you, I'll see if I can do that with you another time. This idea, right? This is really important. Okay, maybe we'll do that at the beginning of the next video. Okay, so last thing before we move on to osmosis, okay, which I'm going to stop there. We'll do that for the next video. All right, so if you have a multiple choice question like this, list the following aqueous solutions in order of their expected freezing points. So aqueous solutions mean that the solvent is water. Water has a freezing point of 0. So my question is, if I put these materials, right, these substances, whether they be ionic or molecular, and I put them into water, which one is going to have the lowest freezing point and then go up from there? So start at the lowest one and go up to the highest one, right, in the order of their expected freezing point. Okay, so what's going to affect the freezing point? Well, first of all, the molality. These are all molalities. So if these were all molecular substances, right, that I got one particle for each unit that I see here, then I would just start with the lowest number and work my way up, right? But that's not the case. Some of these things are ionic, okay? And if they're ionic or a strong acid like HCl, we know that strong acids and ionic substances, when they dissolve, they completely ionize in solution. So I have to count up, take into effect my I, right? What is I? How many particles I get per solution, and then multiply that by my molality, and that times the freezing point depression constant. But remember, the freezing point depression constant is the same for all these. So all I need to know is, what is the molality of particles? So where do I get that from? Well, calcium chloride has 3 particles, so it has an I of 3. 3 times 0.05 gives me 0.15. So how many moles of particles do I get? I get 0.15. Okay, let's do the rest of them and then we'll compare. Whoever has the highest moles of particles is going to be the one with the lowest freezing point. The freezing point is going to be depressed the most. Good? So this guy's 0.15. Okay, NaCl, that is an ionic compound, so I is equal to 2. I get a sodium and a chloride, right? I was 3 here, I is 2 here. So 2 times 0.15 gives me 0.30. So this guy beats out the first one. Okay, HCl, strong acid, you learned in Chem 1, right? We had about 5 strong acids, HCl, right? HBr, HI, nitric acid, and sulfuric acid, right? HNO3, H2SO4 for the first H coming off, okay? So those are, and perchloric acid, HClO4, okay? So those strong acids that you learned in Chem 1, they're going to completely ionize, and HCl is one of them. So what's I2? 1 for the H plus, 1 for the Cl minus. So 2 times 0.1 gives me 0.2. So of the 3 that I did in the top row, who's winning? He should have the lowest, followed by her, followed by her. Good? All right, 2 more. Sugar. Sugar does not ionize at all. It stays molecular. So I is equal to 1. So 1 times the molality gives me just that same number. So this guy's only 0.1. So far, he seems to be in last place. Last, acetic acid. Acetic acid is an acid, but it is a weak acid. So weak acids don't ionize very much. Only ionize about, this guy ionizes about 5%. So essentially, I is equal to 1. Maybe a teeny bit more than 1 because it ionizes a little bit. Okay, so acetic acid is the acid that's in vinegar. I just take the concentration of the vinegar solution times 1, so I get that guy, right? So 1 times that gives me that. So now, looking at here in pencil, I just have to go from highest concentration will have the lowest boiling point. This guy should have the lowest boiling point. Second, 0.3 is bigger than 0.2, followed by 0.15, followed by 0.1, followed by 0.05. So 1, 2, 3, 4, 5 with 1 on the bottom, followed by 2, 3, 4, 5 would be the expected boiling points. Okay, let me see if I make a little chart for you. They're all going to be slightly below 0. Here's pure water. Here's a thermometer, right? Here's pure water. This will be 0 degrees. That's the boiling point of pure water. Okay, all right, take our 1, 2, 3, 4, 5. They're all depressed. They're all slightly less, right? Well, 1, right? This guy had the strongest number, biggest number here. 1 is going to be depressed the most. The freezing point of number 1 would be down here, followed by 2, followed by 3, followed by 4, followed by 5. They're all going to be slightly less than 0. They're all going to be negative numbers, okay? And that's the order that they're going to go up. And here's going up all the way up to 100 degrees C. Okay, so that's for pure water. So does that make sense? They're all below. Okay, I'm going to take a break there. That's 54 minutes. That's a good time for a video. We'll do osmosis next. Okay, no osmosis Jones. And I'll also see if I could come up with one of those practice questions that I was talking about. Oh, you know what? I probably have one back here. Okay, so the interesting thing is you can do that for osmosis as well. You can use osmosis as a way to calculate molar mass. So if I have one of those, that might be sufficient. So let me see what I have. I'll make one up. Okay, great. Thank you. See you next time.